Good afternoon. So we will begin today a couple of lessons designed to learn integration techniques. Slightly fancier than the U substitution. Now I want to give you a little bit of a motivation because obviously in practice you will not use all of these techniques with the same frequency. I would say that the most encountered technique is the use substitution, and the integration by parts, which is the topic of today's lesson, also comes very close to that technique. So I would advise essentially to know very well these two integration techniques, the use substitution and the integration by parts. You will also have to learn some other fancier ones, but later on for the fancier ones, at least try to remember how the general technique, and then you can go back to the textbook if later on after you finish this class you may need to refer back to those integrals. It's true that in practice you often use the computer algebra systems to compute these derivatives. Remember that everything should go through your brain, especially for simpler problems in which it's faster to do it on paper immediately, and also to make sure you don't have computer errors, right? So, I mean, if you know the theory behind the problem, you can essentially double check to see if there is a programming error. So, I mean, don't be in the situation in which you would trust whatever the output of the calculator gives you. It can be as simple as a mistaken input or a number that give you a wrong answer. So, if you don't have a way to actually verify at least partially the answer, then there will be a problem later. So that's one of the motivations for learning this. So going back to the integration by parts, the idea, it's very simple, and many beautiful things in mathematics come from very simple ideas. It's essentially a integration of the product rule. So you basically take the product rule from calculus 1 and integrate it. Now, of course, the goal is to invent a integration technique that will basically help us to figure out the integrals of some problems that cannot be solved otherwise. So we will see how that will play out, because if I just give you the product rule and I say integrate it, it may not be obvious why that's good for our purposes. You know, the purpose is to find other integrals. So remember, from calculus 1, if you have two functions of a variable x and you multiply them together and you want to compute the derivative, the product rule states that this is f prime of x times g of x plus f of x times g prime of x. All right, so let's integrate both sides of this equality with respect to x. So, in other words, we find the antiderivative of this. We integrate both sides. So that means on the left side, we have the antiderivative of a derivative. So we integrate the derivative of a product. So remember, if we integrate a derivative, you get the same thing, right? So that means on the left side, we have f of x times g of x, which is equal to the integral, let's see, yeah, the integral of f prime of x times g of x dx plus the integral of f of x times g prime of x dx plus a constant of integration, but I'm not going to worry about now, so don't worry about plus c. We add it at the end. All right, so let's actually write down, in terms of these terms here that we have here, let's write down by itself this term here, the first one on the right hand side. So that means the integral of f prime of x times g of x dx is equal to f of x times g of x minus the integral of f of x times g prime of x dx. Believe it or not, this is the version that I actually use. There's another version, but this is the most practical one that I use for what we call the integration by parts formula. And it's not going to be obvious what this achieves until we get through some examples, because on a first look at it, you may say that what's the big deal? You just write an integral on the left side in terms of another integral. If anything, it looks like you have more stuff on the right hand side. I don't understand what's that about. Well, the main idea is that by doing this, whether you have a easier integral on the right, so it's not an issue of whether you could use this formula in many situations. You could use this formula for any quantities like this that come from the product rule. But of course you will use it, and it's practical to use it, only insofar that this second integral is easier to solve than the first one. So that is basically the first integral, let's say the given one, or the given problem. You will basically do the integration by parts only if by doing so you obtain a problem that is easier to solve. And I'm going to show an example in which clearly the integration by parts doesn't work, not because the formula is not true, but because it doesn't give you an easier integral to solve. Furthermore, let's analyze what the formula by integration by parts actually does. It takes the original function in this format. So basically it will be your job to recognize or to write your original problem in the form of a product between a derivative, f prime of x, and another function, g of x. And by doing the integration by parts, notice that the derivative moves from f to g. So if you look at these two terms, the derivative moves from f of x to g of x. So therefore, the method works only if g prime of x is easier or simpler than g of x. I put this in quotation marks, easier, because I mean there could be interactions between other functions. So the whole point is, does it get easier? The whole problem, not just g of x, right? I mean, does it get easier if we move the derivative from f to g? Or in other words, if in your original problem you somehow magically, instead of g of x, you end up with the derivative of that function, does that sound or does that look like the problem gets easier or harder? If it gets easier, then chances are that integration by parts works. Sometimes it's not going to be that easy to figure out until you actually do it to see if the integration by parts works. With a little practice, you could tell very quickly that it will work. So without further ado, let's do an example or two, and then I'm going to give you the other version of the formula, which I would kind of discourage you to use because this is much more practical and faster, the one that I just gave you here. But you're free to use either of the two, it doesn't matter for me. So as an example, let's do the integral of x squared times ln of x dx. And let's not rush, okay? Let's analyze why this would be suitable to do it by parts. So first of all, other methods don't work. U substitution doesn't work. If you denote u to be ln of x, then you're going to have an exponential. You're going to get something that you won't be able to integrate right away. But it's very suitable for integration by parts. Why is that? Well, if you think of ln of x as your g of x, now here I purposely arrange it to follow x squared. It doesn't have to be that way. It can be in any order here. But if you look at ln of x as your g of x in the formula in integration by parts, you can anticipate that g prime of x being 1 over x is going to be an easier function to deal with, especially because it's combined with x squared And that's essentially a power. So basically you can anticipate that you're going to deal with, in the end, with x to some power. So if I replace ln of x with the derivative of ln of x, if I do that by legal means, right, by applying this integration by parts formula, chances are that my integral will be easier to solve. But now we have to proceed carefully to actually set it up for the integration by parts. Notice that the formula requires that the other function, in my case x squared, needs to be written as a derivative. So before I proceed with the integration by parts, I need this x squared to be the derivative of something. Right? I need to put it in the proper form for the formula. So before you apply the integration by parts formula, you do an integration step right away here. How do you write x squared as a formula? Well, as a derivative, well, you're going to have to basically figure out its the antiderivative. You have to replace it by the derivative of its antiderivative, essentially. And you should do this in your mind, because in most cases you could do this in your mind just to save, just to not make too much of a mess on paper. So you need to write x squared as a derivative. That means you integrate that in your mind. That's 1/3 x third. Now your function to integrate is in the proper form for the integration by parts. F prime times g of x times dx. And from this point on, the hard part should be over. Well, more or less, we'll see. So according to the formula, this is equal to f of x times g of x. F of x was what's underneath the derivative, so 1/3 x third times g of x, which is ln of x, minus the integral, and now we switch the derivative from the first term to the second term. And again, you could do this faster, but I just want to emphasize how the formula works. And let's separate this part here, and then so it's going to be 1/3 x third ln of x minus the integral of 1/3 x third, and now the derivative of ln, which is 1/x dx. Okay, so now we have some simplification. Let's move the 1/3 out the integral. X third over x is x squared. So indeed, notice that the integral that was on the right hand side is going to be easier to solve. So the integral of x squared is x third over 3, and you're nearly done, right? We can maybe simplify a little bit. Here it's x third over 9, and then plus a constant c. All right, so before we move on to other examples, let's review briefly what the formula tells me. As long as my integral, again, can be written as a derivative times a function, then you can think about integration by parts. But you should do it only if by switching the derivative from one function to another, so basically having f and g prime, gives you an easier function to deal with, and that depends on the context, depends on the example. Once you do that, then you can proceed. Once you make up your mind what g of x is, there's a little integration step, because you need to write the other term as an integral, as a derivative. So you integrate that term and you write it as a derivative of that integral. In this case, x squared was replaced by derivative of 1/3 x third. Once it's in the proper form, then you apply the formula and then solve the second integral that comes up on the right hand side. And don't forget, of course, to carry over the term that appears also outside the integral, which is f of x times g of x. Now remember, practice is everything. Once you go over these solved examples, move to the homework quickly, so you can fix everything in your mind. Let's do another quick example, couple of other examples, obviously, and then we'll talk about some other version of the formula before we call it a day. So stay tuned. All right, so more examples. It's important to notice that the order of the terms here doesn't have to be f prime g. You could also have f g f prime of x. So remember the order of terms in the product, the order of the factors, it's commutative. I mean, it doesn't matter. So don't get stuck into the idea that the role of g of x in the formula is the part attached to d of dx. Essentially, you look at the function as a product of two functions, right? So you're looking at the factor that gets easier via differentiation. That is the key thing when you practice with the technique. What is the factor that gets easier if it becomes differentiated? That is the guy that plays the role of g of x. So here's a quick example. That's second example, I guess, if we count. The antiderivative of x times sine of 3x. Now, should be clear for everybody that of these two factors, x and sine of 3x, x is the one that gets easier via differentiation. If you really want to put it in the order like in the formula above, you can write as sine of 3x, and then x, I put it in parentheses just to emphasize the two terms here. You shouldn't do that, you shouldn't need to do that, but just to make the point. It is x that will be nice if it's replaced by a derivative, because it becomes 1, so you're left with some trigonometric function. Sine of 3x cannot be g of x. If you differentiate sine, you end up with cosine of 3x, okay? So same, a different animal basically, right? I mean, it's not any easier. Okay, so once you identify that this is your g of x, your goal now is to write sine of 3x as f prime of x. So this is where those quick substitutions come very, very handy and time saving. So normally here, in order to find the antiderivative of sine of 3x, so you could put it in the form of a derivative here, you will have to use a u substitution. You take u to be 3x, you do du equals 3dx, blah, blah, blah. So because it's just sine of 3x, just a constant times x, remember the reverse chain rule and the fact that the integral of sine of x is minus cosine of x. So therefore the integral of sine of 3x will be just minus 1/3 cosine of 3x. So it's minus cosine of 3x, but times 1/3 in front of it. And then times x dx. Let me write it one more time here, so because it looks kind of squished here. So minus 1/3 cosine of 3x times x dx. So now this is in the proper form to proceed with the integration by parts. So outside is just f times g. You may want to put again x in front of the cosine so that it's not confusing. Because if I put cosine of 3x times x, it may look like the second x is inside of cosine. And minus from the formula, there will be double negatives here. So keep in mind there's minus from the formula. The integral of, and now we move the derivative from minus 1/3 cosine of 3x to x prime dx, which is going to be 1, right? I mean, we could have just written 1 and be done with it. So we have minus x over 3 cosine of 3x, x prime is 1, minus minus becomes plus, and I can take 1/3 out, cosine of 3x dx. Again, another quick substitution. The integral of cosine is sine. Because I have 1 cosine of 3x, I have another 1 over 3 from that substitution, from that reverse chain rule, plus a constancy. So when everything is said and done, it's just minus x over 3 cosine of 3x plus 1 over 9 sine of 3x plus c. So let's do another quick one, and then let me think a little bit. Yeah, let's do another quick one, and then I'll give you the other version of the formula. Some other integration by parts are a little bit trickier in the sense of not maybe noticing them right away, but they're not actually harder. In fact, they are easier than what I showed you before. They are a little bit trickier because on the first look at it, it doesn't look like you have two functions multiplied together. So here's a typical example, which is sometimes actually given as a basic derivative, like to be memorized, but I don't require that. So what if we want to integrate ln of x dx? It may not seem that it's suitable for integration by parts because it doesn't look like we have two functions, f prime of x, g of x. But never forget that constants can be functions themselves. So it should be obvious that if I differentiate ln, so if I replace ln by the derivative of it, maybe I get an easier function to integrate. So ln will disappear if it's g of x in the formula. The confusion usually is, what is f prime of x? Well, f prime could be just 1. Nothing wrong with that. So you could view this as 1 times ln of x times dx. Nothing wrong with that. So if you want to use integration by parts and you're looking at ln of x as playing the role of g of x, there's nothing wrong to call 1 that constant that can be multiplied with any function. Nothing wrong with viewing that as the derivative of a function. In fact, not only is nothing wrong, it's actually easier than before. Because now, how do we write 1 as a derivative of a function? Like, 1 is the derivative of what? So I'm making a pause here, and then everybody now should just jump and say it's x prime, right? So 1 is the derivative of x. And this is now suitable for integration by parts, just like all other examples. So once again, outside is going to be f times g, that's just x ln of x, minus the integral of x. Now we move the derivative from x to ln of x. The derivative of ln of x is 1 over x dx. X cancels, so you're left with the integral of 1 dx, which is just x. If you decide to memorize this is fine. I don't memorize it myself, right? I mean, you can write it like that if you want. It's just one application of integration by parts. All right, so let's stay tuned for the next part. Again, I strongly advise you to get used to this format of the integration by parts. Strongly advise you, because it's the time-saving thing, basically. I mean, because if you end up doing many times this type of techniques, like U substitution, like this one, you want to have basically a habit to choose to use the most efficient way to go about, especially if you have to use it multiple times in the same problem. But because some people prefer the other version, and some other people actually learn the other version in previous classes, if you learn this, let's say in high school, and you take this class again, I'm not going to forbid it, so I'm going to go over it. It's not really a big deal. It just basically takes slightly more time because of some extra notations. So stay tuned for the next part, next page. All right, so this is the other version of the integration by parts formula. It's just a more systematic way of splitting that function into two pieces. So you basically look at the function to integrate as the product between a function and a differential. Basically the part containing dx. So you basically look at the two parts and one of them contains dx. I'll go over actually an example I've done before just to see how it works. So you split your function to integrate, split it into two u, and importantly that part should be easier after differentiating it. So that part should be easier after differentiating, and dv is the remaining part containing dx as well. So it's not really a much big of a deal, except that you take these functions separately, and one is differentiated, one is integrated. So let's actually see how this works with a previous example that we've done, just to see the whole concept here. So in the previous previous pages, we did the integral of x squared times ln of x dx. So who gets to be u is the function, the part, the component, the factor that should be easier, the other way around, I'm sorry. That should be easier via differentiation. So u will be ln of x, dv is x squared including dx. So actually let's write it in a different order just to make it clear. ln of x, x squared dx. So u should be the component that gets easier via differentiation. The remaining part including dx, it's called dv, which is the differential of another function v. So you have two functions, u and v, one by itself and the other one in the form of a differential. What you do after that, you take separately these two functions. So u is ln of x, dv is x squared dx. Then you compute du, so you differentiate. So du is going to be 1 over x dx. And then you integrate to get v. Right, so you move from dv to v by integrating x squared dx, which was 1/3 x third. And so then you proceed with the formula, the integration by parts formula, which states that outside the function, you write u times v. So that's x third over 3 times ln of x, minus the integral of v du, v is 1/3 x third, times du, which is 1 over x dx. So you split it in u and dv such that u is easier if it's differentiated. You differentiate u to compute du, you integrate dv to compute v, and then you write on the right hand side u times v outside integral, and then minus the integral of v du. If you have to memorize, this is probably easier to memorize, as you know, u dv equals u times z minus the integral of v du. So sounds a little bit faster to memorize. It's not no big deal in my opinion, but some people prefer. So then this is going to be 1/3 obviously x squared. We did this before anyway, so from this point on it's the same. So then it's 1/3 x third over 3 plus a constant c, which is x third over 3 ln of x minus x third over 9 plus a constant. Now, the only difference from the previous method and this one is that you don't bother with taking these extra notations. So this part going from dv to v, in the previous case, we did it automatically, right? So I mean, in the previous case, that was already done when you wrote the integral as f prime g. So the fact that you wrote that component as f prime, it's equivalent to you going from dv to v. Then going from u to du, it's part of the process in the previous formula when you switch the derivative, because that's what you do here. You basically switch the derivative from one factor to another. I'm going to do the rest of the examples with u and dv if you prefer, but I have to tell you that I like to use the previous previous format, and I kind of nudge my students to do that because it just doesn't always seems to me too much of a hassle with these notations. But again, you could do that, no problems. Let me do one example in which you have a definite integral, Riemann integral. See how we play with integration bounds. And I'm going to show you, I'm going to finish with another example or two, which are more interesting in terms of integration techniques. So probably, now that I think about it, probably you should take 2 lectures for this one, if you cannot do it in one sitting. So let's do one more before I move to another page. So suppose I've gotten, what is this? See, this will be example 4. So suppose I want to compute the integral from 0 to 1 t e to the 2t dt. And at this point, you should probably pause the video and see if you could do it yourself, at least the antiderivative. And try not to ignore this advice of mine. Really pause it and do it, and then continue, see if you get it, because practice is important. So just like before, obviously t is best if it's differentiated. So if I use u and dv formula here, I'm going to take u to be t, dv is the rest of it, and then du is 1 dt, and now I integrate dv, so that's going to be 1/2 e to the 2t. So the formula of integration by parts, if you have integration bounds, is not really much of a difference. It's the same formula, except you carry over those bounds. So just don't forget the bounds. In this case, if you prefer, you can handle the bounds at the end, and I'll do that actually myself sometimes. The bounds won't change. It's not like in a substitution in which you change the bounds of integration, so you don't have to worry about that. So you have u times v, which is 1/2 t e to the 2t between 0 and 1, minus the integral from 0 to 1 v du, which is 1/2 e to the 2t dt. So right now, sometimes I actually prefer to plug in the bounds right away, even before I do the second integral. It's really up to you. 1/2 times 1 times e to the second. And then when I plug in 0, that's just going to be 0. And then I'm going to continue with the other integral, which is 1/2 outside, and the integral of e to the 2t gives me another 1/2 e to the 2t between 0 and 1. So here I'm left with e squared over 2, and then minus, here it's important to use parentheses, because when I plug in 1 and 0, and then minus between them, remember there's a minus in front of this integral. So I have 1 over 4, you can put that constant outside, but then it's e to the 2t between 1 and 0, so that's e to the 2 times 1 minus e to the 2 times 0. Make sure you don't mess with this double negative. So that's e squared over 2 minus, now you can distribute 1/4, so it's 1/4 e squared, and then plus 1/4 e to the first, which is 1. I can multiply this by 2. That gives me e squared over 4 plus 1 over 4. 2 over 4 minus 1 over 4. 1 over 4 plus 1 over, yeah, e squared plus, so e squared plus 1 over 4. Right, that's the answer. All right, so I'm going to finish up with 2 fancier examples just to see how sometimes you can combine techniques into more than one technique into the same problem, and that'll be enough for today. All right, so another integral that is not obvious whether it's suitable to do by parts or not. So the antiderivative of inverse sine of x, or arcsine. The only way to go about by parts, and again I'm going to use this time the integral, the formula that I used before. Actually, let me think a little bit. Yeah, I'm going to use the one before. So f prime g equals f times g minus the integral of f g prime. So I'm going to write the integral as f prime times a function. Now obviously the function, to be easier if it's differentiated, you'll see it's easier as a form of speech basically. It's easier than inverse sine, but it's not going to be that easy to continue. It's still easier than just in this format because there's nothing else to do. But the only choice is to have g of x to be inverse sine. So I view this as 1 times inverse sine of x dx. This is my g of x, and I should view 1 as f prime of x. So in order to write it as such, I'm going to write 1 as x prime inverse sine of x dx. And now I proceed with the integration by parts. So that's going to be x times inverse sine of x minus the integral of x times the derivative of the inverse sine. Okay, so now the derivative of the inverse sine, it's okay if you forget it. I mean, these are sometimes not easier to memorize because they are not used that often. So I should put here the derivative sign, right? So the derivative of the inverse sine is 1 over square root of 1 minus x squared. So I have x times 1 over square root of 1 minus x squared dx. So it may look like we get something more painful than before, but it's not really the end of the world. I mean, it's not really that bad, because if you look carefully, this is actually now suitable with a u substitution. So sometimes it's still work to be done, but you still see the light of the end of the tunnel, so to speak. Except now we need to handle this second integral, and the only way to handle is via a u substitution. And the reason it works is because we have 1 minus x squared under the radical, and then du is minus 2x dx. And the fact that I have x dx on the outside of that radical makes that suitable for a u substitution. Of course, I need to move the minus 2 over, because in the problem I have just x dx. So let's continue from the left, carry over the first term, and that's going to be 1 over square root of u, and x dx is minus 1/2 du. All right, so let's move the minus 1/2 outside. Minus minus becomes plus. 1 over root u is u to the minus 1/2. Then we deal with the power rule. Let's see, leave some room here. Minus 1/2 plus 1 is going to be 1/2. 1 over 1/2 is 2. Go back to the original variable. So u to the 1/2, it's 1 minus x squared to the 1/2. So you go back to u, right? Replace u by 1 minus x squared plus a constant c. All right, so try to go over these steps slower if you want to. I mean, you have to. Remember, the rule is to solve on your own all solved examples to practice. But go over the computation yourself. You normally avoid in the exams, maybe with 1 or 2 exceptions, but in general, I don't give problems that are too long, but it's important to point out that these techniques appear more than once, and sometimes they combine different techniques in the same problem. So let's do one. I mentioned more than once, right? So here's a problem in which integration by parts appears more than once. This is another strong argument for using this format of the formula, not u and dv, because it becomes too tedious if you do that. So let's say you want to integrate x squared sine of x. At this point, it should be obvious that g of x, it should be obvious that x squared is your g of x. So let's write it in a different order just to match it with the formula. This is your g of x because clearly if I differentiate g of x, which is x squared, I get 2x. But see, this is the part that may seem a little bit strange, because you may think, okay, if I can't integrate x squared times sine, how come why would I be able to integrate x times some other trigonometric function? Because after all, if I differentiate x squared, I get 2x. But at this point, you should also have the answer by, inquiring this, by putting yourself this question. Because if I obtain x times the trigonometric function, nothing stops me to do again another integration by parts. And if I choose g of x to be x, that x will disappear. So in other words, this is basically suitable for integration by parts, but you will have to do it twice. And it'll be obvious in the process why it's going to work that way, right? If you do that. Now, first thing first, before we proceed, we need to write sine as a derivative. The integral of sine is minus cosine. Apply the formula, minus x squared cosine of x on the outside. Move the derivative from minus cosine of x 2x squared. So that's going to becomes 2x. I strongly advise you to move out the constants to clean up those terms before you move on. So I have minus minus becomes plus, 2 outside. So 2 integral of x cosine of x dx. And now we do it by parts again. Again, g of x will be x. So I'm going to write cosine now as a derivative. So this is your g of x, this is your g prime, this is going to be your f prime of x. So how do I write cosine as a derivative? Well, that's the derivative of sine. And g of x is, like I said, x. Right? So now I finally use integration by parts again. But remember, this time around, there's 2 in front of the whole thing. So open a big pair of parentheses. So x times sine of x on the outside. Move the derivative from sine to x. So that's going to be the integral of sine of x times 1 dx. And now I'm nearly done. The integral of sine is going to be another minus cosine. So it's going to be minus 2 minus cosine of x plus a constant c. And finish up. Okay. So I'm going to do another example. This is a fun example actually, because it's one of its kind really, and we'll see, maybe I'll add more examples later on, just so in a different video. This is basically a fun example because it's one of its kind, and it's pretty much the only example that you will encounter in this class in which integration by parts works, but in a strange way. It doesn't give you the answer directly, and it's because of the nature of the derivative of the function involved. So let's see our last example, and this one you shouldn't worry about too much. You might see it in the homework. I don't usually put it in the test because it's really one of its kind. There are versions of this, and it's still something important to know because there are not too many examples that work this way. And let's actually denote the integral that I want to find by I, and you'll see why that's actually important. So the quantity, the antiderivative that I want to find, I'm going to call that I, and the integral to compute is of e to the x sine of x dx. So it's not obvious if it works with integration by parts, and here's the reason why. Doesn't matter which one you pick to be g of x. If you differentiate either of them, you don't seem to get something easier. If I differentiate e to the x, I get e to the x. If I differentiate sine of x, I get cosine of x. But try to anticipate, and it doesn't seem to be any easier to integrate e to the x cosine as it is to integrate e to the x sine. But think further a little bit and realize that if you do it again by parts, if you have e to the x cosine and you do it again by parts, you're going to go back to the original integral. So you basically may be able to solve directly from for that integral as you solve an algebra equation. So you do it by parts twice and you obtain something in terms of the original integral, and you will be able to compute it at the end. So it's one of those things in which you have to have a little faith and see how it works, because it will be clearer at the end why it works that way. And I should mention here, in this case, it doesn't really matter which one is g of x or f of x. Just make a choice and stick to it. So I'm going to make a choice that the trigonometric function is my g of x. So therefore, I'm going to write the first function as a derivative, which in this particular case is the same, right? It's e to the x prime sine of x. And I do it by parts once. And then switch the derivative. So that's going to be e to the x times the derivative of sine, which is cosine of x. And I'm going to do it by parts one more time. So I'm going to view again e to the x as a derivative. So carry over the first term. Open a big pair of parentheses here. So that's going to be e to the x cosine of x on the outside minus the integral of e to the x, and again move the derivative to cosine. So that's going to be minus sine of x dx. So let's clean up a little bit these terms. So e to the x sine of x minus e to the x cosine of x. Then it's going to be minus minus minus. That's minus integral of e to the x sine of x dx. Okay, so notice that we started with a quantity that we called I, the integral of e to the x sine of x, on the left side. And we concluded that this is equal to e to the x, let's actually put e to the x here. So e to the x times sine of x minus cosine of x minus the same integral that I tried to compute. So this is also I. It's the same integral. You basically wrote the same integral in a different way. Okay, so by applying integration by parts, you concluded that I is equal to some function minus I. So magic question, what is going to be I equal to? Well, I'm just going to solve for I as I normally solve an algebra equation. I'm going to move I to the right hand side, so I'm going to treat that I as an unknown. Divide by 2. So I, which was again the integral of e to the x sine of x dx, is 1/2 e to the x sine of x minus cosine of x plus a constant c. All right, so I hope you enjoyed that. Versions of this which you can practice is to replace x with any constant times x. So you could do this. It will work the same way, but it'll be a little bit more tedious because you're going to handle some constants each time when you apply this integration by parts. So that's it for integration by parts, and I'll see you next time.